Hi there, I'm Stephan Lavavej, and since we're finishing up development on VC11, now branded Visual Studio 2012, I'm once again free to bring you the second part of my video lecture series on the core C++ language, Part 2, Template Argument Deduction. As I explained in Part 1, when you call a function, a bunch of things happen in sequence. Part 1 was name lookup. And then today we're covering template argument deduction. And then this is followed by overload resolution, which after the compiler has found which function names, you've named a function, so the compiler has found all of the possible things you could possibly try to call. Template argument deduction, which is what we're seeing today, has filled in any missing template arguments, and then they all enter into an arena and battle it out in overload resolution. So either one will emerge the victor, or an ambiguity will be declared, and basically everybody ends up dead, and you have a compiler error. And then other things happen, like access control, virtual function calls, which we'll be seeing. So template argument deduction, I find this process to be sort of entertaining. It plays a simple game, which we'll be exploring, and it can seem sort of complicated at first. I find it's very simple, whereas once we get to resolution, that has a bunch of fiddly little rules, which are hard to keep track of, even if you got the standard sitting in a separate window. Figuring out exactly what the compiler is doing can be tricky, whereas with template argument deduction, it's almost always obvious what the compiler going to figure out, even though there are subtleties that we'll get into. So why does the core language have template argument deduction? Well, it enables a bunch of cool things. It's for efficiency. That enable you to write code which work at compile time. So when a template is instantiated with template arguments, it's essentially stamping out object code, machine code, that's customized to the specific types involved and any operations, like function objects, and anything else that you might be customizing with an algorithm or a container, things like that. This is more efficient than attempting to provide such genericity with mechanisms like virtual function calls. Before the STL was actually invented, when people said, oh, I want a container, they would say, oh, I need to make all of my elements derived from a common base type like object. And then the container will store object stars. Because how else could I write a container that'll work with an infinite universe of element types that people might want? That was terribly horrible. And STL showed us the right way to do it, use templates, where that genericity can be compiled out, and you end up essentially with a dedicated class or dedicated algorithm to some type that the library author had never seen. So this enables us to write code that is as efficient or sometimes even more efficient than handwritten C code. The classic example of that is when you write a std sort, and the comparison functor that you're giving it, less than, greater than, or some custom comparator, can be inlined. And that inlining enables incredible compiler optimizations that the ancient C function qsort, which takes a function pointer, can't do because qsort is separately compiled whenever your toolset author built their standard C library. So efficiency is good. It's also convenience. Because it would be terrible if whenever we had to call a function templates, we had to manually specify every single template argument. The compiler already knows the type. It's right there. I just declared it above, or it's in the type of the class. Just figure it out. We've seen this in C++11 with auto, where the compiler knows the type of an initializer. Can't you just make the destination type be the same? Template argument deduction is essentially an earlier form of that in C++ 9803. In fact, auto is powered by template argument deduction. So if you want to understand how auto behaves in tricky corner cases, first you need to understand how template argument deduction behaves. And finally, Yes, it can be somewhat tricky, so it is rather good for programmer employment, but that's not its primary purpose. It's complicated because C++ is a large language. There's lots of things that can go on, and programmers want to express very subtle things. The idea behind things like template argument deduction and overload resolution is that the programmer is writing potentially very complicated code, and the language should just do the right thing. And therefore, it needs rules which end up being inherently complicated to deal with this. C++ is not going out of its way to throw a ridiculous 1,000-page rulebook at you. It's just what naturally arises in the course of trying to make things like this work. So today we'll be looking at all the subtleties of template argument deduction. Here's a simple example. So the series is about the core language, but I'll be using the STL from time to time for examples because A, it's already available, and B, it's chock full of templates, which is a lot more convenient than attempting to write example code by hand. So here I got a vector. I'm going to go sort it. Here I'm using template argument deduction, and this is happening, among other things, in the call to sort. So sort is an STL algorithm. It's templated on arbitrary iterators pointing to arbitrary elements, and it can also take a custom comparator, although in this case I'm calling the default version that sorts with less than. So here, sort v begin v end. What's the signature of sort? I could go look it up in the standard, or IntelliSense will tell me what the declaration looks like. If you look here, unfortunately I can't hover over it. I guess I can point to the TV. It says template on class random access iterator stood sort taking 2 random access iterators. So sort is templated on iterator type. This could be a vector iterator. It could be a dec iterator if we're using that strange container. It could be a std array or even a raw pointer. The STL totally works with raw pointers. They're totally reasonable random access iterators. They're actually sort of the most powerful. And yet when I called std sort, I didn't need to tell it the iterator type. It was deduced for me. If I wrote it out, the type would be, erase this, the type would be vector of int iterator, like this. That's sort of a mouthful to type. And yet, the compiler already knows the type of my iterator. How does it know? Well, I declared my vector v, and the return type of v begin is vector int iterator. So when I call sort, the compiler should really just be able to sort of fill in the blanks, and it does. IntelliSense is nice enough here to show me the instantiation of sort with the type filled in. It's also showing the true name of the vector iterator. The actual type of vector iterator is unspecified. It could be a raw pointer. In VC's implementation, it never is. It's always a class type. And in VC10, it has the true name of underscore vector iterator with a bunch of guts. This has actually changed in VC11. This allocator has been removed thanks to scary iterators. This type is totally implementation defined. It can be referred to with the portable type def vector int iterator. Users are never supposed to say this horrible type. But either way, having to specify the type would be very verbose. So template argument deduction simply fills it in. That's great. But how does that work? Well, let me get rid of all this standard library code, and let's go to a more simple example. Okay. Oh, here I had, of course, just included all the headers that I need. I'll just minimize this now. So imagine that I've got a template on some type name. Why is this expanding? What? Oh, because I'm typing a declaration. You can tell I don't code in the IDE. Template type name t, void, let's choose a name at random, and let's just take a t by value. Okay. And then I can do something like print t. So this is a simpler example than what I was just doing with the standard library. And so if I have something like this, then I can compile and run this. And I get the expected result, 1729. So if I hover over meow here, come on, give me IntelliSense. Okay, it's not giving me IntelliSense. It probably has to parse something. It's going to deduce t to be int, because the type of 1729 is int. So how did it figure this out? Now, I could have explicitly specified the template arguments. You've probably seen this. What this would look like is putting some angle brackets here and saying, I want to actually call meow of int and give it a 1729. This will also compile and run. I don't want end to continue. There we go. And it'll print the exact same thing, but this is more verbose. And if the type involved is something like vector int iterator, it's terrible. It's actually a deep principle. Our compiler front-end developer, Jonathan Caves, once explained this on our internal C++ mailing list. He said, don't try to help the compiler. And it actually took me years before I really understood what he was saying. And template argument deduction is an excellent example of this. I have seen people time and time again run into trouble trying to specify explicit template arguments when they would have been much better off simply allowing template argument deduction to do its job. It can cause all sorts of issues, such as constructing the wrong type, giving you compiler errors, causing problems with internal helper functions. There are times and places to use explicitly specified template arguments. Those times are usually when you must provide an explicit template argument, like in make shared, where you've got to specify the type that you want constructed. But in many cases, the vast majority of cases, you just want to use template argument deduction. Don't specify anything that you don't absolutely have to specify. So explicitly calling meow int here, that's not a good idea. If we simply say meow, it figures out that t is int. So how does that work? Well, let's flip over to the standard here. Here I've got the current working paper for C++ 11. The current draft is N3376, which is freely available on the committee's website. And it's got this actually extremely useful list of bookmarks over here. So if we go over to clause 14 out of 30 in C++ 11, templates. This is all the language for all of the templates in the core language. Sitting in 14.8, there is a section called function template specialization. So I won't go into all the details of the standards here, but it is useful to know when you're reading standards. The standard authors and compiler developers speak slightly differently than most programmers you'll find, even library writers. Most programmers, when they see something like sort int or vector int, they're going to say, oh, that's an instantiation of a template, because the template, it's a cookie cutter. When I go stamp out a class or a function and I get that delicious cookie, I'm instantiating the template. This language it's right, and it's totally unambiguous, except that it's not quite what the standard uses. When the standard sees something like vector int, it says, oh, that's a class template specialization, and it's essentially as good as an ordinary non-templated class. Or a meow of int, when that template argument has been supplied or deduced, that's a function template specialization, as good as an ordinary function, essentially. Even though we're not explicitly specializing anything with the syntax template, empty angle brackets. So the standard says specialization, where most programmers would say instantiation. It's just something to be aware of. The standard is a little more precise, even though it causes confusion. So that's why it is hiding under this apparently slightly misnamed section here. And then 14.8.2, template argument deduction, is the section that we're interested in. And there's a couple subsections here, deducing template arguments from a function call and deducing template arguments from a type that we'll be very interested in. So I'm going to collapse this bookmarks down so we can see more of the standard here. Hopefully this is sort of large enough to read. Yes. So this here, I encourage you to read along with me, pause the video if necessary. This explains how, given a declaration of a function template, which is something you've either written yourself, like in my template type name t void meow here, or that a library author has written, like we saw with sort, and an actual call, like the sort vbegin vend I had earlier, or meow 1729 here, what template argument deduction does is, I like to explain it as it plays a little game. It looks at the function arguments, the things that you're actually providing, whether they're vector iterators or integers like 1729 or custom class types, and then it looks at the function parameters which the template is taking that involve template parameters. So the parameter is the thing that is in the function declaration. The argument is what you're actually giving it. There's function parameters and template parameters, function arguments and template arguments. It's good to keep them all separate. And by comparing the function parameters to the function arguments, it can figure out what template arguments would be necessary to make those types exactly match up. In this case, it's extremely simple because we've got meow taking some arbitrary type t, the type actually being passed as int, so the compiler can see, oh, you must want t to be int. But in fact, template argument deduction can do lots more complicated things. if the parameter type, the function parameter type, is something like, oh, I'm going to take some pair of x and y, and the argument type is actually a pair of int and short, then template argument deduction will reach in there and it'll say, oh, your template on x and y, x must be int and y must be short, and that is going to cause these types to exactly match. It can also handle cases where the parameter being taken is, say, a const pair xy ref, and the actual argument type is a pair in short. It can say, okay, I don't really care about the reference and the const, and yeah, I see you've got a pair here, x must be int, y must be short. So it's essentially applying human intuition to figure out what template arguments you really want, but it's doing so through a completely cold, ruthless set of rules that are specified in the standard. And the rules can be sort of scary at first, especially because now in C++11 you've got stuff in there about initializer lists and variadic templates, which you can skip over until Visual Studio implements them. Or you can read C++03 because the rules haven't really changed here, except for the expressions finding, which is C++11 specific. So these 14.821 and 14.825 in the current draft, they explain this process that I just explained in convenient English, where it does this matching between function parameters and function arguments. And then it will go into the type and reach in. So we can get a little more complicated. Now I'm going to start to show you places where template argument deduction will fail and why it would fail. So imagine that I had meow here, and instead of taking t, I could do something like template on type name t, taking t1 and t2 like this, and I can print out both of them. Okay, and then I can call meow with something like 17 and 29, and build, and it compiles, and I get 17 space 29. So in this case, template argument deduction succeeds even though it had to match two different function parameter, function argument pairs. It looks at t1 here and says, okay, I've got a t and you're giving me an int, cool, t must be int. And then I've got a t2 and you're giving me an int, okay, t must be int. So looking at each pair of function argument and function parameter, it's derived the same type for t, int, and they all match up, it's all consistent. So the two pairs have produced a single template argument, we succeed, and we actually call the thing. However, this will fail if the function parameter argument pairs lead to different results for t. So I could screw this up by, instead of giving 17 and 29, what if one of these is a long? So I can attach a suffix l to any integer literal to make it of type long, or I could put ul for unsigned long. You've probably seen that in C or C++. So if I attempt to compile this, oh, look, IntelliSense is always already squiggling. IntelliSense will tell me error. No instance of function template meow matches the argument list. And the actual compiler, if I attempt to build this, will fail, telling me, let me see, can I expand this? No, just widen it some more. It says, void meow tt, template parameter t is ambiguous. C declaration of meow, could be long, could be int. So you've probably heard people love to insult template errors. They say, oh, it's an error novel, the thing is like 100 lines, and it's horribly complicated, and there is a lot of truth to that. But the compiler is not going out of its way to spam you with obnoxious information. And it's also not just for programmer employment. It's because if you want to understand when a template is failing to compile, the error could be when you actually tried to call the template. It could be within the template's guts itself. The template itself was written wrong. Or it could have happened anywhere along the way. If you're calling a template that instantiates another template and so on and so forth until you actually get to the destination, something could have gone wrong. Something could have diverged between your intent and the actual code that was written. And if you want to figure out what's going on, the compiler needs to tell you what it was thinking, because there's no way to debug into the compilation process unless you're a front-end developer. So in this case, this error is giving me additional context. It's telling me the site of the function call, this is line 13, saying, okay, I can't compile this function call because I don't know what the template parameter is. It's ambiguous. But then it's also going to point to the definition of the function, that's line 8. And it's going to say, okay, go look at the declaration, and by the way, here's what it could have been. If there were more levels of context here, functions calling functions calling functions, then this would expand and expand. But all of the information is actually useful. It just takes some experience to learn what to focus on and then what to skip over. I always focus on both the side of the call and the actual place where it's exploding, and then I try to see quickly if I can fill in the blanks and say, oh, you know, obviously I meant to do X. Sometimes both those sites look okay and the explosion is actually in the middle, in which case diagnosing it can be fun, but that happens more rarely. So in this case, let me minimize this. I actually like VC's error a little better than EDG's, but we're probably chopping out the additional context here for IntelliSense. This function argument is of type int, so t is deduced to be int, whereas this one is of type long. So this one deduces t to be long. So the two pairs have produced differing answers for t, and whenever this happens, the compiler is going to say, I don't know what t is, it's ambiguous. So it's going to throw up its hands, it's going to give you a compiler error, it will not attempt to say, oh, if I chose t to be long, then one would be an exact match, and the other one I could convert and that would widen, so I guess that looks okay. And it's certainly not going to say something like, oh, I could choose t to be int, and I could narrow from long to int. It's technically a narrowing conversion, and then it would still really be callable. No, template argument deduction does not play such games. It simply says, does this match? Okay, are all of the answers consistent? Cool, let's do it. If not, ambiguous. So that's why I think of it as a relatively simple process. There are ways to make this sort of thing compile. If we really want to design a template like this, we'll see how that works. So this would happen if you try to call something like sort. Remember how sort, here I'll just scribble it on the board. Actually, instead of sort, let's use a better example, like countif. So if I'm doing like countif, okay, this takes a couple iterators, and then this takes a predicate, and it will tell you how many elements in the sequence match the specified predicate. So I would usually say countif, vbegin, vend, and then something else. However, if I were to pass it something like vbegin, and then instead of vend, if I said vcend, and then whatever, the type of this is vector iterator. I can't spell. And the type of cend, this is a C++ 11 function, is const iterator. And yet, countif is templated on a single iterator type. It is a input iterator. So if I give it vector int or whatever iterator and vector int const iterator, these are different types. So there's no single type that countif could deduce without resorting to conversion. So this will be declared to be ambiguous. You'll get a compiler error. So if I wanted to make this actually compile, I would need to either say begin and end, making them both modifiable iterators, or I could be very careful and I could say vcbegin and vcend to get const iterators to make the types match, because countif is not interested in actually modifying the elements, it's just inspecting. So if you mess up the types that you're feeding to a template, you can get these sort of ambiguities declared because of template argument deduction. Remember, it's trying to simulate human intuition, but it's working through a set of rules. So if it can't see what you want, it will say, oh, you know, I'm not going to compile. It's not just going to sort of charge on ahead and say, oh yeah, you know, I can totally choose the right type here. So that is how matching works. And yeah, I wanted to show you dropping constness. So imagine that instead of a call like this, let me get rid of a couple of these here. One, print one. Okay. Imagine that I had something like int n is 24, and I called meow with n. This will compile and work. So I can make n const here. Okay. Then within here, I could say something like, oh, let's take, I'll just call this t. T times equal to. Okay. So without actually compiling this, you might wonder, okay, so I've got this n. Its type is const int. So if I try to modify n here, it will totally fail to compile. I can prove it. I could say, hey, n times equal 2. And this is totally bogus. Hey, I'm already getting squiggled. It's saying error, expression must be a modifiable L value. N is const, can't go modify it. So if I pass it to meow, without knowing all the guts of template argument deduction, you might expect, oh, well, n's type is const int, so t's type should be constant, so I shouldn't be able to modify it and then print it. That would be bogus, right? Well, actually, this will totally compile and run successfully, and I will get 2, 4, 6, 8 printed. Yes, I do. And there's a reason for this. So what's happening here is that given the parameter type, in this case, tt, okay, and given the function argument type, const int, okay, I'll get rid of the name here of the variable. The name doesn't matter, okay. What template argument deduction is, it says, okay, I see that the parameter type is just an ordinary value. It's not a reference or anything. And the argument type, okay, it's a type, but it's top-level CV qualified. The standard says CV qualified when it really means const or volatile. Even though volatile is extremely obscure, they behave, and it behaves in extremely similar ways to const. So both const and volatile are lumped under the banner CV qualifier. It says, okay, we've got a top-level CV qualifier being matched against just an ordinary value. You know, let's drop that. Let's just pretend that they were passing an int, and okay, then t will be int, those types will exactly match. Let's do it. So it's dropping const, and because within meow, it takes, after template argument deduction and substitution, it takes int t. That's a totally modifiable int. I can modify a function parameter like that, so I can double it and then print it out. So the rules say this. I could go point into the standardies. Why do they say that? Well, if I've got some local variable like constant n, and then I pass it by value to a function, I'm copying the value. Even after modifying t here, we know that out here in main, I'm not directly modifying n. I'm not taking a reference or anything. I'm modifying a copy. So whatever the function meow does to its copy is totally unrelated to the source. So why shouldn't it be allowed to modify? Because when I went and declared meow, or in my definition here, I said I want a modifiable t. So that's why the constants of the source is disregarded. It's going to be dropped. But of course, this does not apply if I take references. So if I said meow and I need to take a t ref, and I want to write through to the given t, this will horribly fail to compile, saying, whoa, t is being deduced to be constant. You can't modify that. Yeah, so I get build failed. And if I expand this out, it's saying here, t, you cannot assign to a variable that is const. Oh, and it's telling me with that wonderful template error, see reference to function template instantiation void meow, and here it's writing it with explicit template arguments to show you what the type is, const int. So this rule about dropping constants only applies when you're calling a function template that's taking a parameter by value. If it's taking a reference, then argument constants is not dropped. Precisely because this would be a horrible safety problem. If A's type is constant and P's type is tref, it says, okay, you've got a reference to t. I'm going to sort of ignore that reference. I'm going to look at the t, and I'm going to match it without modification to this constant. So I'm going to end up with a const int ref, which is what you would expect. Now, it's always okay to apply constness. So if I have meow here, and if I don't attempt to modify this, and I say, okay, I'm going to take const tref and call it with a constant, t is deduced to be plain old int, and the actual parameter here that I'm actually taking is const int ref, and everything is good. If I were to explore t in here further, by giving it to a class template, I would see that it's literally just int and not constant. I could also say with a value const t and then print it out, and I will actually swap this. If I've got a modifiable int here, I can increment it just to prove that it's modifiable and get rid of some of this white space. And compile and run. Everything's good. And I get 1, 2, 3, 5. In this case, I've reversed what's happening. So if I've got a modifiable int as my function argument, and the function parameter, the destination, is a const value, then when attempting to match up the types, what template argument deduction says is, okay, your P is a const value, const T, and your argument A is int. So its usual mechanism is to make the types exactly match. But when it sees a value that's top-level CV qualified, what it says is, oh, you definitely want to copy this thing, so the constantness of the destination is unrelated, as we just saw, to the constantness of the source. So even though the source is modifiable, the destination, the function template, says, I'm not interested in modifying this template argument, so I should totally be able to compile this. So it's going to ignore the top-level const, and it's simply going to say, okay, I can deduce T to be int, and everything's cool. So that can be responsible, like in this case, it's doing exactly what we would expect. But this can cause sort of interesting behavior that you might be surprised by if you were to inspect T through other mechanisms, like giving it to a class template. You would say, wait, you know, why is T int and not constant here, or vice versa? Well, that's what template argument deduction is doing. In the standard, I can show you what the standard is looks like. This looks like it's function call. There's other contexts in which template argument deduction runs, like taking the address of an overloaded function, partial ordering, more and more complicated ones. But function calls are the majority way to trigger this process. Skipping over some C++11 stuff, we can see here, yeah, here's the rule that I was talking about. It says if the function parameter is not a reference type, meaning it's just a plain old value, then it does a couple things. It decays arrays, it decays pointers, and if the argument is top-level CV qualified, this is the case where you're passing it a constant and you're going to copy, it says, okay, I'm just going to ignore those top-level CV qualifiers of A's type. I'm just going to pretend you're passing a modifiable in because you're going to be copied anyways. And then alternately, when constantness is on the destination, it says if the parameter, the function parameter is top-level CV qualified, I'm going to ignore that too. Again, this doesn't apply to references. References always preserve that constantness there. It's only when you're copying values. So standard is, it's very dense, but what it's doing is this sort of very simple thing. If you've worked with templates at all, you already have a very solid intuition for how template argument deduction works. It's just looking at all of the subtle rules that power it can be very interesting. It's like, oh, I never knew that it could do that. So one of the reasons that template argument deduction is so successful and that it just works and that you can actually just start using it almost on day one of learning how to program C++ is because it's so powerful. The matching game that it plays can really reach into a type and dig out all of the template arguments that are in there. There's actually a list in the standard of all the actual contexts in which template arguments can be deduced. And here is the list here. It's huge. Plain old types, pointers, references, R-value references, function types, pointers to members, pointers to member functions, arrays, actual templates, and then you've got your template non-type arguments, your template arguments. That's not a typo. It'll reach into all of these things and perform its matching game. So you can feel sorry for the front-end developers who have to actually make all this stuff compile. But as users and as library developers, if you're one of those, you just get to enjoy all of this wonderful technology that the standard is specified and that the compiler devs have implemented without worrying really too much about how the compiler is reaching in there and doing this matching. However, there are some situations in which the compiler will not consider performing template argument deduction, and the standard is for that is a non-deduced context. It says, okay, in some situations, looking at a function parameter and a function argument pair, I'm not even going to attempt to deduce what template parameter is there. So I can show you an example of this. Imagine that I have, let me get type traits here. Again, I'm just using this standard library stuff because it is a convenient source of pre-existing templates. And let me just simplify this down. Suppose I've got just a straight up int. Okay. And meow is going to take, I've already using stud. So type traits, as we saw in an earlier STL series, allows you to manipulate types at compile time, and it does this through helper structs with nested type defs. So I could say something like, oh, I've got some arbitrary type T, I would like to make that const, or remove any constants, or make it a reference, or say, okay, is this thing a reference? I could also do things like make this signed, make this unsigned. So within meow, I could totally do something like take a t and then say, I would like to have a u variable that is, I'm just going to essentially cast it, but I need to figure out what that is. I could say, if I want to be really precise, static cast 2u of t and print out whatever u is. Okay, what's u? I could say type def, and then I need to say type name disambiguation. I'm already using stood, so I could say make unsigned, whatever the type is, of t type as u. And suppose I was passing in a negative number here, then I should actually get a very large positive unsigned number printed. It compiles, and indeed I do. So this is negative 1, 2, 3, 4 converted to unsigned int. So this works. However, what if I tried to say, okay, in meow's signature, I want to actually just take make unsigned of t type, and suppose I'm just going to say, okay, I know I'm going to need to say type name here. This will not compile either way. And then I don't need any of this. And then t here. This will not compile. And here we go. I get a build failed. So the squiggle is going to tell me no instance of function template meow matches the argument list, just like earlier we saw when I passed it conflicting arguments to a two-argument function and it couldn't figure out what t is. In this case, it's also saying it couldn't figure out what t is. And if I look at the build compiler, it says error, meow, could not deduce template argument for t. See declaration meow. So it's saying that template argument deduction, which is actually mentioned here, template argument deduction, is failing. It just can't figure out what t is. And you might expect, you know, why doesn't it work? Because template argument deduction works in every other case that I can possibly think of. I mean, look at the standard here, the list of types, the list of situations in which template argument deduction can dig out the right answer is enormous. So why isn't this one of them? Well, it isn't. And that's actually specified. There's the list of non-reduced contexts. Here it is. It's actually listed here. So the standard is if you've got a nested name specifier of a type that was specified using a qualified ID, that's a non-reduced context. So that probably sounded like Klingon. What this really means is that template argument deduction, the way I put it, is it will not look through double colons. It won't look to the left of them. It's a brick wall to template argument deduction. So if I say something like, I'm just going to skip over the type name. If I say something like make unsigned of t type, okay, if this is a function parameter and the argument is anything, it could be int, it could be unsigned int, whatever, template argument deduction just statically looks at the type of this function parameter and it says, oh, you're actually reaching in to some, in this case, a struct template and getting a type def, but you had to use a qualified ID or this double colon here. So the presence of that double colon means the template argument deduction will not attempt to deduce t here. It has to be found out through other means, either explicitly specified, like I mentioned a while ago, or found through another function argument, function parameter pair. But in no event will this pair be used to deduce what t is. So it doesn't trigger failure, but it's not going to find out t itself. This is true regardless of what type is actually being passed in here. And this rule can seem a little harsh, but if you think about it, it makes sense. Because imagine in this case, let me just get rid of some of this. Okay, what make unsigned really is, and it's not specific to make unsigned, it's true for everything. It's mapping. It's mapping the source type to destination type. So in this case, it is, if the source here and the dest is here, then if the source type is int, then that gets mapped to unsigned int. And if the source is unsigned int, no underscore, that's also mapped to unsigned int. But if the source is something like short, then this gets mapped to unsigned short. Okay, so imagine that you were actually passing an argument of type unsigned int. What should it deduce t to be? Well, passing unsigned int to make unsigned would give me an unsigned int. Passing int to make unsigned would give me an unsigned int as well. So if the function argument is something like this, then, you know, or if the destination type is that, how could it possibly figure out what t would be? There's multiple right answers for t that would result in the types matching. So the compiler essentially throws its hands up and it says, I can't possibly figure out what t is. How can you expect me to do this? You're trying to reverse something that's not exactly one-to-one. So template argument deduction, we'll just skip over this. It's not deduced. And this is true regardless of what make unsigned actually does. You could have a struct template that does do a one-to-one mapping of types, but template argument deduction will still say, you know, I'm not going to do it. And this actually basically never causes problems, except when people try to get tricky. Let's go back and imagine that you've got something like, suppose that you're writing an algorithm and you're saying, oh, I want the algorithm to work for arbitrary vectors, but I don't want it to work for other containers. There could be a reason to do that, maybe. You could say, okay, template type name t, and then I'm going to have some function f, and I'm going to take a vector of t iterator first, and then blah, 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 same for last. I can't spell. L-A-S-T. And then whatever. And attempting to actually call f will fail, because if you pass it a vector int iterator, it can't deduce what t is, because you've got this double colon here. In this case, it could really be an S type or could be a type def, but template argument deduction doesn't care. It just sees that double colon, a qualified ID, and says, okay, that's a brick wall. You know, I have X-ray vision, but I just can't see through that sheet of lead, so you're going to have to tell me what t is, or it's going to have to be deduced from something else. I am not going to figure it out here. So this could cause trouble when you start to write advanced templates like this. However, it can be used for a trick. This recently came up on our internal C++ mailing list, and I can show you how this works. Let's see, I'm going to need functional. And template type name t, and I want to take t by value, and then I want to take a stud function, which is a polymorphic function wrapper. Again, standard library machinery, we don't really care what it's doing here. It's some just arbitrary function with a signature that returns, let's say in this case it's going to return int, and it's going to take int. No, it's going to take t. I'll make it void. It's similar to the original one. And I could pass it by const ref, which I really would in normal code. I'm just going to take it by value here for simplicity. And then I'm just going to invoke f on whatever the val is. I'm just going to assume that the function is non-null. And then I've got, I don't even need a local variable here. I'm going to pass this some arbitrary number, picked at random, and then a lambda function where I'm going to take some int x and then print, hey, I'm a lambda. I'll put a space here to be nice, and then x. Okay, lambdas are core C++, but I won't be covering them today. It's an object of a unspecified compiler internal type. You literally can't name it except through decal type, or if you look at, or auto, or if you look at what the debugger is saying. So here, IntelliSense is helpfully squiggling me, telling me its usual, no instance of function template meow matches the argument list. Gee, thanks. If I try to compile it, I'll get the exact same error saying that it can't figure out what t is. It's actually going to talk about std tier 1 function, because in vs10 that was the true name. Could not deduce template argument deduction. Could not deduce template argument for std tier 1 function void t from, here's that unspeakable type, anonymous namespace lambda 0. That type is actually different in VC11. So template argument deduction, why aren't you coming to the rescue? We just saw all the wonderful things you could do, and I don't even have a double colon here. I'm saying, you know, function void t. Now you might ask, you've got this class template, stood function, and then you've got this weird sort of thing here. This is a function type, which is not ordinarily seen outside of stood function. And yet, instead of putting the lambda here, let me comment this out because I want to preserve it for a second. And instead, if I had this and I passed it a fxn, and I said, I want a stood function with the signature void int, and I'm going to initialize it from this lambda here. This should work in VC10. It totally compiles and runs, and I get lambda 1729, which is what I wanted. So if I have a named variable, or a temporary would also work, whose type is literally stood function taking int and returning void, then template argument deduction is absolutely willing to match it up and say, okay, here's meow, 1729 is of type int, t-val, t must be int. Let's match the other pair. Here's a stood function, and its type is actually function taking int, returning void. Here I've got a function taking t, returning void. T must be int. That would make the types exactly match. Both pairs give me int. Awesome. T is int. Let's go party. Yet, if I passed a lambda, which can be used to initialize the stood function, it totally compiled here. If I try to do this directly, it will not work. So why doesn't that work? Let me get rid of this. Okay, here's the call that didn't work, and I get the squiggle. The reason why is, as I mentioned, template argument deduction plays a straightforward game. It tries to match the provided function argument type to the function parameter type, and tries to pick template arguments that will make those types exactly identical with a little wiggle room for adding consonants, adding references, decaying arrays to pointers, and things like that. In this case, what's happening is the parameter type is stood function, returning void, and taking some arbitrary t, and we want to figure out what t is. And the argument type is some unspeakable lambda. We saw it was lambda 0, which you can't actually name. So there is no choice of t that will make this type equal to this type. Period. Full stop, end of sentence. And template argument deduction says, I can't figure out what t is. And that actually makes it fail. And if you think back to the whole sequence of steps, if template argument deduction fails, this overload is not added to the overload set. Because I'm not covering overload resolution, I've not provided any other overloads of meow in this case, so there's just no function to call, and that's why we get this compiler error. If instead there were other competing overloads of meow, they might win, but in this case, I've only got one, so that's why it fails. Template argument deduction does not consider any conversions, even though you can convert lambdas to functions of this signature, or as we saw, you can convert ints to longs and things like that, or const char star to basic string. What happens is template argument deduction says, I don't care about conversions. That's overload resolution's job. I don't do that. I simply make one type equal to another. I can't make these two types equal. Sorry, you're out of luck. And yet in this case, information for what t is available through this first parameter t-val. So there actually is a trick to make this compile. Now, I could use explicit template arguments to make this work. I could say, okay, meow, and by the way, t is int. But like I mentioned, explicit template arguments are not a good idea in the vast majority of cases. So if I want to make this compile without that, I can use, here I'll show you what it looks like, because it's technically non-standard, thanks committee. Template type name t, struct identity. So identity is going to be the simplest metaprogram ever. I take some arbitrary type and then I spit it right back out. Type def t type. I'm just capitalizing it here to show that it's really not part of the standard. And then instead of taking this, because my screen is tiny, I need to go like this. I'm going to instead take identity of function void t. I can use angle brackets. And then I need to say type name double colon type. Now I said double colon there. Remember, it's a brick wall, and this is actually a feature, not a bug in this case. f. So yeah, this declaration looks horrible, but let's see what it does. Okay, that looks like it should work. Compile, and it builds, and it runs, and I get lambda 1729. So I made the original call compile without tweaking the call at all. I didn't need to provide explicit template arguments or anything. I simply modified the template definition. So in this case, remember that this double colon inhibits template argument deduction. What I said is, okay, I want you, the compiler, to match up this t-val to whatever value is being given. And that'll deduce some t, or not if it fails. But in this case, it'll totally succeed, and I'll get an int. And then I've got type name, identity, blah, 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 double colon. I wish I could just highlight this in red. So when template argument deduction looks at the type of f here, it says, oh, that's a qualified ID. I'm not going to try to figure out what t is from this pair. I'm not going to fail. I just need to figure out t through other mechanisms. And it did, through val. So if val's template argument deduction succeeds, the deduced template argument for t will be substituted into this horrible looking type here. And it says, okay, function void int, I'm going to feed that to identity, get some type back out, it's the same type, and then that's the type of f. So I get an actual signature. And the signature that template argument deduction spits out is meow taking int and function void int. Then we go into overload resolution, blah, 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 and then we get an implicit conversion from this lambda to the stood function type. That's just an ordinary function call. We know how implicit conversions work. The thing is actually callable. We've gotten past the step of template argument deduction. So in certain advanced cases, using this rule that double colons inhibit template argument deduction can be extremely powerful. When I posted this on our mailing list, I just sent essentially this example saying, oh, you just need to use this. And that was followed by a 30-minute to an hour exchange of mails where other developers like, what, how did that work? Because when you've never seen this trick before, it's crazy. But then you can surprise your friends with this later. So I'd also mentioned other implicit conversions. The other case where you'll often see template argument deduction fail is when you're working with like arbitrary strings. Let me show you that before I finish. So I don't need any of this. Delete this. I do need to include string. There's been talk in the committee of providing a stood all header that would simply include every single standard library header for you. That has not yet happened. There's been talk of modules in C++ 22 probably, where you would have a standard module and you could just drag everything in without actually including it in your translation unit. The core and evolution language designers are considering that. As a standard library developer, I'm like, great, when it's done, tell me how it works. Too complicated for me. So here I don't need identity. And if I had template type name, oh, it's going to insist on expanding that. Suppose if I said, I'll just say t, even though I would usually say char t. Suppose that I want to work on arbitrary character types, and I'm going to take, I'll just say const reference, const basic string of t, and then I don't care about the trace, I don't care about the allocator, ref, s, and I'm going to print that. So imagine that I just want to handle narrow strings, wide strings, char 16t, char 32t when we get that from C++ 11, or other PODs. Plain old data, and I could say, okay, I want to call meow, and then suppose I have a string handy, string s, like this, and then I pass meow s, and this will totally compile and work. And it does, and I get Peppermint, the name of my cat. So this works because the typedef string is really a typedef for stood basic string of char. So template argument deduction, it doesn't care about typedefs. Typedefs are always transparent. It only cares about the true type that's being passed. So when it sees the argument, the function argument, basic string of char, and it sees the function parameter, const basic string tref, it says, oh, if t is just plain old char, then I can make these types essentially identical, except for the reference and the const, which are cool. So t is char, and then let's actually call this thing. What if, however, instead of this, I try to directly pass meow of Peppermint? So I could be using wide chars, but that's not of interest here. This will not work. And I'm already getting a squiggle. You can guess what error it is. And it says no instance of function template meow matches the argument list. And the actual compiler will again tell me that template argument deduction fails and it can't figure out what t is. And it's just saying C declaration. So it's sort of always spitting out the same error when template argument deduction fails. That's because the compiler, it's not a human. It's not as smart as we are. All it can do is play the type matching game. And if that fails, it's got to throw up its hands and say, I can't figure out what it is. And yet this can be caused by a bunch of different things like double colons as we've seen, the two types being different, or in this case, the actual type of peppermint is a const array of char of n number of characters. I'm not going to try to count them, plus the null terminator. But you can think of it in this case as a const char star. That's what an array is after it decays. There is no choice of t that will make basic string of t exactly identical to const char star, even though const char star is convertible to basic string of char. We just saw that template argument deduction does not consider implicit conversions. So that's why this won't work. So in this case, the way that this is always handled in the standard library, which has things like f-streams and regex, especially regex, is when you want to have a function that's templated on arbitrary basic strings, you should provide an overload that's templated on arbitrary const char stars. So if I also add template on type name t, void, here's an overload, we're sort of getting into part 3, const t star putter, and then people complain when I pronounce ptr as putter, would you believe that? And I say cout, and I'll show you that we've got a different overload here. I picked that up from our front-end developer. It's a way to abbreviate pointer when it's not spelled out in full. And here I could say string, stir. If I save and compile, this will work, and I will see putter peppermint. Yes, I do. So in this case, what's happening is name lookup runs, everybody's in global scopes, that's cool. Well, not cool, we know namespaces are good, but in examples it's totally cool. Then template argument deduction runs, and it runs for every possible candidate that was found through name lookup. Here it sees, okay, you're calling meow, I see 2 meows, so I need to figure out what template arguments you want so they can go compete in overload resolution. If there's any plain old functions, those immediately go to overload resolution. There's no template argument deduction for them. So in the case of meow taking const basic string ref, template argument deduction still fails. And it says, okay, const basic string t ref and const char star essentially, I can't make these types identical, so I don't succeed with template argument deduction and I don't give anything to the overload set. It's not a compiler error. It would be terrible if we got a compiler error here for something that really should compile. So it just doesn't go to overload resolution. Then template argument deduction runs for this other candidate, and it says, okay, I want to make const t star equal to const char star after array decay. And yeah, I can make these identical if t is just char. So this one succeeds, and I get the overload meow const char star sent off to overload resolution. And in this case, only one survived. So it wins by default, the 2 greatest words in the English language. And this one is chosen, it's actually invoked, and we get this printed out. So you'll see things like regex and other headers always overload things on const basic string of char t and const t star. That's why, because otherwise things just wouldn't compile. You'll notice this is also good for efficiency. Even if I could make the overload for meow of const basic string ref compile, usually that would require a temporary to be generated from a const char star or string literal, and that temporary is totally unnecessary if I'm just trying to print something out. Raw string, plain old C strings are terrible, but if you've already got one, then why make a stood string? So that's why such overload sets exist. It's both for efficiency and for correctness, so that the thing will actually compile and work. So that's basically everything I want to show you today. In part 3, we'll go over overload resolution, in which all of these plain old functions and function template specializations, or instantiations if you want to think about it that way, after they've got their template arguments filled in, they go off into the arena of overload resolution, and the compiler considers, okay, I've got all of these actual function arguments and function parameters, and I may need to perform conversions. Which conversion is the best? The programmer's throwing all these overloads at me. What should I do? And overload resolution has a whole clause full of rules that tell the compiler which overloads to consider better than others. That's where a lot of the complexity of C++ comes in, and we'll see how that works. So if you have questions about what you'd like to see there or in other parts, send them to me in the comments. Until next time, see ya.